Okay, in this video we're going to look at some of the basic principles of Newton's universal law of gravitation. Up here you see some important numbers and constant values. It's good to have this table handy. You have the gravitational constant, the radius of the Earth, radius of the moon to Earth. Now the difference between here is the radius of the Earth, we're talking about the distance from the center of the Earth to the edge of the Earth. Now that's a mean distance over the whole circumference. Now the radius between the moon and the Earth, this is really what we call an orbital radius. So if this is the Earth over here and this is the moon somewhere over here, this is a center to center distance, which we call the orbital radius. So in this unit, whenever we refer to the radius in terms of the universal law of gravitation, it's the center to center distance between two objects. Okay, the mass of the Earth, mass of the moon, the mass of the sun, these are also constants that we're going to use quite often. And then the astronomical unit, if you ever see a unit of an AU, this is the approximate distance between the Earth and the sun. So it's a way of simplifying measurements of length on a solar system scale. Actually, this is 10 to the 11th meters, 1.5 times 10 to the 11th meters, which is a large number. So sometimes we refer to them as astronomical units just to simplify the numbers. Now, what are the implications of Newton's theory of gravity? What you saw in the previous video was about how Newton thought through this relationship, really the inverse square relationship. But his universal law can be summed as a way of quantifying the magnitude of a force interaction between all objects with mass. What we've observed is that the universe with objects of mass will always see this apparent attractive force. So if you put two objects with mass near each other, they will accelerate towards each other proportional to their mass based upon their presence within the same area as another mass. So it's directly proportional, the value of the magnitude of this force, to the individual masses that are attracted, and it's inversely proportional to the square of their orbital distance, or the distance between their centers. So it's one of the inverse square laws, since it's proportional to the inverse of the distance in between them. So there's another force that behaves in a similar manner, another force of nature that we are going to cover a little bit later, and that is the electric force. And the electric force is based upon the magnitude of the electric charge of an object. So Q1 and Q2 are electric charges. Say like a proton is a positive 1 charge, an electron is a negative 1 charge, and they have a value in coulombs, which you'll see when we get to that unit. But notice the similarity between the two equations. They're both inverse square laws. The magnitude of the force depends upon how much charge or how much mass there's present, and the inverse square of the distance between the two, which I think is kind of significant because these are two of the forces of nature, fundamental forces we call them. Now there is one large difference between the two, and that is that the electric force is way stronger than gravity, on the order of 10 to the 32nd power times larger, or gravity is 10 to the 32nd times smaller than electric force. So gravity is a very weak force, especially along small distances. But what happens over large distances, like the scale of the solar system or the scale of the universe, is that gravity takes over. And it has to do with the fact that gravity always attracts. So two masses will never repel each other based upon this force of gravity. They will always attract each other. But on the other hand, the electric force, sometimes it's an attractive force when you have positive and negative charges, but sometimes if you have like charges, positive, positive, or negative, negative, it's a repelling force. And so what happens is over large distances, these tend to cancel out. So over long distances and large masses, gravity is a dominant force. So it's a force that we study relative to the motion of objects on a solar system or galactic or universal scale. Now, going back to the lab, is this force of gravity acting on both objects in question? So in questions 9 and 11, you're looking at the space probe and the alien ship. And what's true is that if I have the alien ship over here, it's my best flying saucer impersonation, and I have my space probe, which is just some sort of satellite over here, and they're experiencing the force of gravity. That force is a mutually attractive force. So the mutual attraction means that it's a Newton's third law force pair. So when we say, going back to the moon and the earth here, when we say the earth, the moon is attracted to the earth via gravity's pull, the earth is attracted back towards the moon in the same way. This is a mutual force. So if we're looking at what's happening to the motion of the moon, we're interested in the force of gravity between the earth and the moon acting on the moon, but if we looked at the motion of the earth, it would be the opposite. So don't neglect that this is also a force pair. Same force, equal magnitude, opposite direction, acting on both objects. Now, is the acceleration of both objects the same? Well, no. And why is that? Because objects with a really tiny mass will experience a great acceleration from the same force. And objects with a bigger mass are going to experience a smaller acceleration from the same force. So don't confuse the motion of the objects with whether or not there exists a mutual force of gravity. It's just that the objects with less mass will experience a greater acceleration due to that force. Now, last question for this video, why is the gravitational force acting on the moon also a centripetal force? And this is where we start to connect the worlds of universal gravity and circular motion, which we've been studying. So if we look at this Earth-Moon system, where we know the moon is orbiting around the Earth, and there's this mutual attraction due to the force of gravity acting on both objects. This force is always acting towards the center of the objects, and as the moon rotates, it has a tangential velocity, always tangent to the circular path. And as gravity acts on it, that force becomes a force pointed towards the center of the moon's orbit. So because of this, this force of gravity becomes a centripetal force. So because the moon is orbiting in a circle, this force of gravity is pulling it constantly back towards the Earth, generating this centripetal force. Now, how could we figure out the centripetal acceleration of the moon, and why is it not 9.8? Well, remember, 9.8 is an acceleration due to gravity for objects at the surface of the Earth. Now, the moon has some large orbital radius here, RME, which we looked at before, is 3.84 times 10 to the 8th meters, as opposed to the distance from the center of the Earth to the surface of the Earth, which is 6.37 times 10 to the 6th. So it's a much bigger distance. So what happens is, over a much bigger distance, so as the radius increases, the centripetal acceleration decreases relative to that longer range or that greater radius. So the moon does not have the same acceleration as in the surface of the Earth because of the increased radius. So there is a little bit of an intro on the universal force of gravity. In the next video, we're going to look at gravitational fields and gravitational field strength due to gravity.